Okay, so today, since this might take a while, instead of going through the paper, I'm going to do something closely related. So on the first page of this paper about gaps between primes, they reference the Bombieri-Vinogradov theorem, and watching some talks on this, it seems pretty important. So I looked this up, and so I'm going to try to give a brief explanation of what it is, mostly to help myself, but maybe someone will find this useful. So this is following a nice outline by Kantorovich, 2014. You can probably just look this up and find it. He explains it probably a lot better than I will, but yeah, that's life. So, recall from, it's pretty well known at this point, the prime number theorem. So this is pi of x is the prime counting function, which is just basically the sum of the characteristic function of the primes less than or equal to x. So it just counts the number of primes. And this is like asymptotic to x over log x. And this is the prime number theorem. But you can ask, like, how good is this estimate? Like, what is the error on this estimate? And it turns out if you subtract them, it goes on the order of x over log squared of x. And this actually isn't all that great. You can actually do much better than this. So log squared is a pretty slowly growing function, so this is kind of a linear bound. It's not very satisfactory. But it turns out if you, this second version of the prime number theorem, which you can prove, it's a bit more difficult, that it goes with the logarithmic integral of x. And this is defined as essentially the integral from 2 to x of like 1 over log x. And so this, you can kind of think as saying that the local density of primes is 1 over x at x. And so to get the total number of primes, you just kind of integrate this from like 2, the smallest prime, to x. And this, if you expand it out, I think actually turns out to be x over log x, that first term, plus x over log squared of x. Let me just quickly check. Yeah. And then plus like an order 3 term, right? So already you can see that this is kind of just a higher order correction to the like basic prime number theorem. And this turns out to have a much better error. So it's O of x over log to the power of a of x for any a greater than 1. So this is clearly better than log squared. One thing that will become important later in this derivation is, and this explanation, is this big O notation implicitly hides constants. So this is, of course, this is a kind of an undetermined constant here for the big O, but this will like implicitly depend on A. And so that's going to become kind of important later, because ineffective constants a lot of times can hide some pretty nasty stuff. So anyway, with that said, we'll go on to extend this prime number theorem to arithmetic progressions. So instead of counting all the primes less than x, you could just somewhat interesting to count all the primes that are like a mod q for some q, right? And so this is what this pi with the semicolon aq is. It's just the same thing, except you're only counting the primes that are a mod q. And so, well, because these are all primes, they're all going to be like co-prime to q, so they're going to fall into one of quotient of q residue classes. And so since you're only looking at one of them, if the primes are like kind of random on average, like very Dirichlet's, then you expect basically this to be roughly asymptotic to pi of x over like phi of q, right? Because like 1 in phi of q of these primes is going to hit the residue class A. And so it's reasonable to estimate this using like logarithmic integral over phi of q and look at the error of this. And it turns out this is actually a pretty good error. And so you can get this unconditional estimate again, where this depends on A again, of order of A, big O of log x over log A of x. So yeah, that's all good. And if I look correctly, blah, blah, blah. Yeah, this is pretty much good. Oh, and this also depends on q, actually. So that's good to know. Actually, that's important later. But the other thing you can do, so this is an unconditional estimate. If you assume the generalized Riemann hypothesis, which is a big assumption, you can get a much better result, which is that it's just O of log, O of x to the 1/2 plus epsilon. And so actually this, according to the paper, turns out to be quite a common thing, where you have these like 1 over log stuff. But if you assume like GRH, then you can suddenly get like a square root kind of cancellation here, where you get, instead of like log to the whatever, you can get like a 1 over square root x over square root of x, and this gives you the 1/2 plus epsilon. And so, yeah, this is all great. This is an okay estimate, but it's not too good. It turns out it's actually somewhat, in some sense, easier to ask what happens on average instead of what happens at each individual x, so each individual q. So on average, what you can do is you can take this error term from above, put in an absolute value. Of course, you have the max for like all residue classes, so you're kind of averaging over residue classes and then averaging over like all q less than some bound. Not really, it's kind of some, whatever, but big O like hides all of it. And so this you have O of x, so this depends on A, and yeah, if I have this correctly, let me quickly check. Yeah, this should just only depend on A. But essentially, you have this unconditional bound. And this Q, what is it? It's some power of x. And actually, this is what Yitang Zhang was saying when he said like d is some power of x. He didn't mean like integer power, it just means like x to the something. But yeah, if you can take this Q to be x to the power of something minus like a bit of epsilon, and this will hold true for any small epsilon, then this var theta is called exponent of distribution. And this is what Yitang calls the level of distribution. And so like clearly if you take this Q too big, you're gonna like blow over this like x over log a to the x bound, and so you're not gonna be able to get this result. So there's kind of a like limit on the maximum exponent distribution you can have. And it turns out that this is the Bombieri-Vinogradov theorem. Yeah, this is the Bombieri-Vinogradov theorem that exponent distribution of the primes is 1/2. Right? And this is kind of what you'd expect, just assuming the generalized Riemann hypothesis. Actually, let me quickly step back. So why can't you just use this unconditional bound? Well, it's because this big O hides this unconditional constant, or sorry, hides this like ineffective constant based on Q. So if you try to use this bound by itself and just bound each individual term, since you're summing over Q's, like a varied range of Q's, there's no guarantee that these these ineffective constants will actually be bounded in any way. And so you kind of blow over this bound just by using that. If you have the generalized Riemann hypothesis, you can get this x to the 1/2 plus epsilon. And so even though it depends on Q, it turns out this is strong enough that when you sum over Q, even with these ineffective constants, you can still get like order of x over log to the a of stuff, right? So since you kind of need the generalized Riemann hypothesis, or at least the generalized Riemann hypothesis would be a sufficient condition to ensure this with a level, with an exponent distribution 1/2. But Bombieri-Vinogradov kind of gives you this result directly on average, that the exponent distribution is 1/2. And it turns out this is apparently the best you can do. I'm not actually quite sure whether they've proved that you can't do better than 1/2. Yeah, I'm actually not sure. For now, since I'm not sure, I'm just going to assume that it could be also larger than 1/2, like it could work, but no one has proved it yet. But in any case, Bombieri-Vinogradov, all it says is exponent distribution 1/2, which Zhang refers to as the level of distribution. So in this kind of vague sense, I think Yitang mentioned this before as well in one of his talks, that the Bombieri-Vinogradov theorem is in some sense as strong or stronger than the generalized Riemann hypothesis in this very specific sense. So a lot of times when you're looking at kind of distribution of primes and you want to look at basically the prime counting function for some like residue classes and whatever, Bombieri-Vinogradov is a good substitute for the generalized Riemann hypothesis in the sense that on average it gives you the same level of distribution, the same like restrictions on the distribution of primes. So yeah, that's a quick explanation. I might post another video today about going over the rest of the paper, or like starting from where we left off last time, but I wanted to get out this explanation of Bombieri-Vinogradov since it seems quite important precursor of what's discussed in this paper. So yeah, if you found this useful, if you're still watching at all, thanks for watching.